Hello, and welcome to our lesson on the definition of the derivative. So in our previous topic we talked about the difference quotient, and then we talked about the limit of the difference quotient as h is approaching 0. So just a little recap on that because it's going to directly connect to what we're doing with our definition of the derivative. So when we're finding the difference quotient, that's this one over here, remember the difference quotient is just a version of slope. So we could say that m, or slope, is equal to f of x plus h minus f of x over h, where what we're doing when we're finding that version of slope, using that notation, is finding the slope of a secant line over a closed interval, and we're doing that to find the average rate of change of some curve over that closed interval. So we are approximating the rate of change for some function using the secant line. Okay. Now then we said if we're going to find the limit of that difference quotient as x is approaching 0, as h is approaching 0, that is the distance between the 2 points in the closed interval. If the distance between those 2 points approaches 0, then we are instead finding the slope of a tangent line. So an instantaneous rate of change, or the slope at a point instead of a slope over a closed interval. So again, the limit of the difference quotient as h is approaching 0 is another form of slope. It's just slope of a tangent line and at a point instead of a secant line over an interval. And instead of an average rate of change over the interval, it is an instantaneous rate of change at a specific point. Okay, but both versions of slope. So now, what is a derivative? Now, I might have mentioned this at the end of the last topic, but the derivative is the limit of the difference quotient as h is approaching 0. So the derivative of our function, let's just call it f at x, is defined again as the limit of the difference quotient of the function as the distance between x and the next point approaches 0, so as h approaches 0, provided of course that the limit exists. So our definition, what we see here in this box, the limit of our difference quotient as h approaches 0, that is our instantaneous rate of change. It's the same thing. All we're using now is different notation to say, instead of just calling this slope, or instead of saying slope at a tangent line or instantaneous rate of change, we're going to call it a derivative. Okay? But they're all process-wise the same thing. So if I'm asking you to find an instantaneous rate of change, or the slope of a tangent line at a point, I am asking to find the derivative. They're all the same process. So again, just different notation, where instead of just calling this m, we're going to call this f prime of x, and that is notation for the derivative. Okay, let me erase the highlight on this one. Okay, so finding a derivative is essentially the same as finding the slope of a tangent line, or of a line tangent to a curve at a point, or the instantaneous rate of change. Okay, same processes. And again, our notation, f prime of x, that's what we see here, that's how we read that. So we're going to say f prime of x, that is the derivative. So the notation f prime of x is read f prime of x, but the function f prime of x is called the derivative of f with respect to x. Okay, and then just some other terminology here. If x is in the domain of f and f prime of x exists, then we would say that f is differentiable at x. So if we are finding a derivative at x, if we're able to find a derivative at x, then we are going to say that our function is differentiable at x. And also the process of finding the derivative, the process that produces f prime of x, we call it differentiation. That's a long word, trying to sound that out. Okay, so just some, again, vocabulary for you. But the work that we're going to do here is really the same work that we were doing at the end of the previous topic. When we're finding instantaneous rate of change, finding the limit as h approaches 0 of our difference quotient. We are finding a derivative. Now we're just going to call it a derivative. Now, what makes this kind of tricky is some of the algebra can get a little messy, but the way we can ask the question now can vary. So you have to know that when I ask you for all those different things, I'm really asking you to find the same thing. Okay, so let's look at a few examples where I changed the wording, and we can practice with some of our algebra. So let's find some derivatives first. We're going to find and interpret the derivative of f of x equal to x squared plus 1, and then we're going to find and interpret the derivative at a specific point, in this case at x equals 3. So first, let's find our derivative. If we're going to find the derivative, we are trying to find f prime of x, and according to our definition, we're going to find this by finding the limit as h approaches 0 of the difference quotient for our function. Now remember, difference quotient has three pieces. Go back up here for a second. The difference quotient has f of x plus h minus f of x divided by h, those three pieces, okay? So it's the limit as h approaches 0 of our difference quotient. So first, f of x plus h. So we're going to replace x with x plus h. So that's going to be x plus h squared plus 1 instead of just x plus 1. And then we have to subtract f of x. So we're going to subtract our entire function, which is x squared plus 1. And be careful on that step. We want to make sure to put our function in parentheses if it's more than one term, so that both of those terms get subtracted. And then we're going to divide this by h. Now remember, when we're trying to evaluate a limit, we're trying to just plug 0 in to figure out what the value is, but I can't plug a 0 in this form because it's going to make our fraction undefined. So now we're going to do a little bit of work to clean up the difference quotient and hopefully get to a place where we can plug the 0 in for h. So I'm going to change colors here. I don't want to rewrite this limit notation every time. So I'm just going to work on simplifying my difference quotient. So we have x plus h squared plus 1, and I'm going to distribute the negative here. So that's going to give me a negative x squared and a negative 1. And again, this is all going to be divided by h. Now I'm going to distribute the binomial. So we have an x squared, and then I have an xh here, another xh here, so that's two xh's. And then h times h is going to give me an h squared. And then again, I have a plus 1, a minus x squared, and a minus 1. That's all being divided by h. My attempt at drawing a line there, terrible. Okay, so let's clean this up. We have some terms we can cancel, x squared and negative x squared, positive 1 and negative 1, and now we're left with this fraction. And I can actually divide 2xh and h squared by h, so let's do that, which means we're going to be looking finally at a 2x plus an h. Alright, so that's the simplified form of our difference quotient. So really what we're trying to do here, when we're finding our derivative, f prime of x, is we're trying to find the limit as h approaches 0 of just this 2x plus h. Now that's all we're trying to do. Well, now we can easily evaluate this limit. Now that it's in its simplified form, I can evaluate by again replacing h with that 0. So this becomes 2x plus 0, which is just 2x. So we've found f prime of x is equal to 2x, which means we have found our derivative. Okay, so this is the derivative. What does that mean? That means if we were looking for the slope of a tangent line at any point on the curve of x squared plus 1, that's our function, this is the equation we could use to find that slope. So this is the slope of a tangent line at any x value. Okay, so we're going to interpret this. This is the slope of a tangent line at any x. So the next part of this question said to then find and interpret the derivative at x equals 3. So if I want to find the derivative at x equals 3, that means I want to actually plug that x value in. So we're going to call this f prime of 3. We're going to plug 3 into our derivative. So if I plug 3 in, then 2 times 3 is 6. That is the slope of the tangent line at this particular point, so at the particular value of x equal to 3. So f prime of 3 is the derivative at 3. It's equal to 6. So let's say f prime of 3 is equal to 6. And what this represents, again, is the specific slope of the tangent line at 3. So this is the slope of the tangent line at specifically x equals 3. Okay? So 2x is our derivative. 2x is an equation we can use to find the slope of any tangent line at any particular x value. If we input a particular x value, then we have the slope of a specific tangent line at a specific point. So in this case, again, let me just show you this graphically so that hopefully it makes sense, if it's not already. If we graphed x squared plus 1, here's our curve. Okay, what we're saying is at the x value of 3, let me just make a point so you can see it. So an x value of 3, if I plug that into my function, 3 squared is 9 plus 1 is 10. So 310 is the point we're looking at here. If I drew in a tangent line, a line that's tangent to this curve that touches just that single point at 310, its slope would be 6. Okay, that's what we're saying here. And if I moved it to a different point, then the slope is going to change, which makes sense. The slope varies depending on where we are on this graph, but it will always be found by multiplying 2 times x because that's the equation for our derivative. Okay, so hopefully that makes sense. Not really much different from what we were doing again at the end of the previous topic, maybe some new notation, and hopefully a little cleaner organizationally because they got a little sloppy in the end of that last one. Okay, so next one. A little more straightforward, just let f of x be 4 over x, find f prime of x. So we have a function, we're asked to find its derivative, let's do it. Okay, we know that when we're finding the derivative, f prime of x, we are looking for the limit as h approaches 0 of the difference quotient. So f of x plus h, that's going to be 4 over, instead of x plus h, minus f of x, the function itself, which is just 4 over x, divided by h. Now when we're trying to evaluate this limit, remember I'm trying to plug a 0 in for h, but I can't do that. It makes our fraction undefined. So again, I got to do some work to simplify the difference quotient and hopefully get to a place where I can input that 0. So in this case, we saw one like this in our previous topic. I want to actually subtract the fractions that are in the numerator. So I'm going to bring this down here just so you can see what I'm going to try to do. Here's our difference quotient. Let's clean it up. I need a common denominator to do the subtraction, so I'm going to multiply here by x and multiply here by x plus h. And now my denominators match. They both have a factor of x and x plus h. So we're looking at 4x here, and then minus 4x and minus 4h here. And that's going to go over our common denominator, which is x and x plus h. So there's this. Okay, this becomes this one fraction with the common denominator. Now that's still being divided by, not x, I don't know where that came from. This should be an h here. That's all still going to be divided by h. Now we have some like terms. So the 4x and negative 4x will cancel. So now we're looking at negative 4h over x and x plus h being divided by that h in the bottom, which means we actually want to multiply by the reciprocal. So instead of dividing by h over 1, I'm going to multiply by 1 over h, and then we can do some reducing. We got an h in common here. And so we're finally left with the simplified form. We end up with a negative 4 over x times x plus h. So remember what we're trying to do. Trying to find our derivative. So we're trying to find f prime of x, which is the limit as h approaches 0 of our difference quotient. Well, we just said our difference quotient is going to simplify down to this. Negative 4 over x times x plus h. And in this simplified form, I can input my 0. So when I input my 0, then I have negative 4, and notice I'm moving that negative around. It doesn't really matter where the negative is as long as you have it in there somewhere to make the fraction negative. It's going to be x, and then x plus 0. So we end up finally with our derivative being equal to negative 4 over an x squared. And so this is an equation we can use to find the slope of a tangent line, or a line that's tangent to any point on the curve of, what was our function again? 4 over x. So anywhere we are, if I plug in any x value, look at any point that's on this curve, this equation will tell us the slope of the tangent line at that curve. It will tell us the instantaneous rate of change at any point along that curve. Okay? All right, we got a couple of examples under the belt. Let's look at the next one. Again, just so you can see how the wording changes a bit, and so that we can look at a different type of function, just to clarify. The first one was a polynomial function, specifically a quadratic function. The second one is a rational function, or a reciprocal function. This third one we're going to look at here is a square root function. So, example 3, different type of function, but the same concept. It doesn't say in our part A here to find the derivative. It says to find the slope of the tangent line. That's the same thing. Okay, so this is other wording for find the derivative, f prime of x. And then we're asked to find the slope of the tangent line at x equals 4. That means find the derivative at x equals 4. So this is saying find f prime of 4. Okay, and then the last part's a little bit new, so we haven't done this. It says find the equation of the tangent line at x equals 4. So all we've been doing all along is finding slope. Now we want to actually write an equation for that tangent line. So let's get to that in a second. First, what we already know. If I want to find f prime of x, again, I want to find the slope of my tangent line. That's f prime of x, the limit as h approaches 0 of the difference quotient. So f of x plus h, replace that x with x plus h. So the square root of x plus h plus 40. And then subtract f of x, so the function itself, which is the square root of x plus 40. Again, make sure we're subtracting that entire function. And then divide by h. So again, to evaluate this limit, I got to plug a 0 in for h. Can't do that in this form, so I need to try to simplify. So first, I have the square root of x plus h plus 40. If I distribute the negative here, then I'm going to have a negative square root of x and a negative 40, which means the 40 and negative 40, those are going to go away. So I'm going to be looking at the square root of x plus h minus the square root of x over h. So we've simplified by getting rid of the 40 and negative 40, but I still can't evaluate this at h equals 0, so I need to try to manipulate this a little further. And we're going to see happen here what happened in one of our topics. I can't remember which one offhand, but I'm going to rationalize the numerator here. As long as I'm multiplying my fraction by 1, I'm not going to change its value. So I'm going to multiply by a form of 1 that will again rationalize the numerator. So I'm going to multiply by the conjugate of this numerator, that is radical x plus h plus radical x. And as long as I do that on the top and the bottom, again I'm multiplying my fraction by 1, so I'm not changing its value. And so what happens? Let's see. In the numerator, I'm going to end up with an x plus h times an x plus, or radical x plus h times radical x plus h. So think about what we're doing here. That's radical x plus h squared, right? So the square and the square root are going to cancel. That means I'm going to be left with an x plus h. And then when we multiply conjugates, I want to be able to shortcut the work here, but I don't want to lose anyone at the same time. So a little side example here. When I multiply conjugates, so these are binomials that have the same terms but opposite signs, like x plus 3 and x minus 3. It will always happen that we have the product of our first terms, and then a negative 3x here and a positive 3x here that cancel. So a positive 3x and a negative 3x in the middle cancel, and then the product of our last term is negative 9. These will always cancel if these binomials have the same terms but opposite signs. So I really only need to concern myself with the first product, which is going to get me the x squared, and the last product, which is going to get me the minus 9. Okay, so I want to save myself a little bit of work here. Hopefully this is familiar. and it's something you've seen before, and you can save yourself the work as well. So even though it's a binomial times a binomial that contains 4 products, I know the middle 2 are going to cancel. So I want to, again, concern myself with the first product, so the square root of x plus h squared, which is going to give me that x plus h, and then the last product, which will be a negative square root of x times a positive square root of x. So a negative times a positive will be a negative, and again, the square root of x times the square root of x, that's the square root of x squared. That's just going to be an x because those two operations will cancel. So the square root of x squared is just going to be an x, and that's going to be divided by, h has to multiply by this binomial, and I'm just going to leave that as h times that binomial, x plus h, and negative radical x under the radical. Now on the top of the fraction, I can see x and negative x cancel. And so if I'm left with just an h, and then an h in the bottom, I have a common factor of h, which means I can take the step of reducing out that common factor. And so we're going to be left with 1 over the square root of x plus h minus the square root of x. Now this is a form that I can plug, or that I can, where I can evaluate, where I can actually plug 0 in for h and get an equation that, or a fraction that is defined. So I am now in a big mess, finding the limit as h approaches 0 of the new simplified form of my difference quotient is 1 over the square root of x plus h minus the square root of x. Again, this is a place where now I can evaluate. I can actually put the 0 in for h and be almost done with this. So I'm left with 1 over the square root of x plus h will just be the square root of x, and a minus square root of x. That's no good because those would cancel and give me a 0. Did I do something wrong here? What did I do? Cannot see my mistake if I made one. Maybe I didn't make a mistake. Oh, I sure did. Whew, I found it. Okay, sorry, my apologies for the delay. But I made a sign mistake. You see how easy this is to do? And when I multiply here, well, it was a transfer problem. Right here is a positive, and for some reason I made this a negative, and I don't know why. So maybe you saw that and were like, hey, you're messing it up. So that should definitely be a positive there, which will make that a positive there. Whew, I'm like, what did I do? Okay, so I found it. So now those are like terms, not terms that cancel. I have 1 over 2 of those radical x's in the denominator. So we're going to say f prime of x, our derivative, our slope of our tangent line, is 1 over 2 radical x. Man, I'm glad I saw that because I was about to stop the video and record the whole thing all over again. Okay, so we have our derivative. Now part B, we have our slope of our tangent line, our equation for our slope of our tangent line. Part B says find the slope of the tangent line at x equals 4. So now I actually want to find the slope at a particular x value. I'm going to plug that x value in. So again, I want to find f prime of 4, plug that into my derivative. So that's going to be 1 over 2 times the square root of 4. Square root of 4 is 2, 2 times 2 is 4, so that's going to be 1/4. So the slope of the tangent line at this particular x value is 1/4. Now, if I want to find the equation of the tangent line at x equals 4, when I'm writing a linear equation, I'm trying to write something that looks like this, y equals mx plus b. That's what the slope, or that's what the equation of a line looks like. Now, I can only write it directly in that form if I know m and I know b. Now, I know m. I just found it, right? This is my slope at this x value. So I know m, but I don't know b. So I can't write y equals mx plus b outright. But I can use another form of a linear function. So the other form we're going to use, more often is point slope form. So that's y minus y1 equal to m times x minus x1. So if I know my slope, which I do, it's 1/4, and any other point on the graph, which I know, well, I know almost the point, then I can write my point slope form and simplify down to my slope intercept form. So this is the form of our linear equation that we're going to try to write. Okay, so I need three things, well, actually two things. I need to know the slope, and I need to know a y1 and x1, a point on this line. So I know my slope. Found that in the previous problem. I know my slope at the point I'm looking at is 1/4. And I know the point I'm looking at has an x value of 4. I just don't know the y value at that point, but I can find it because it's a point on this curve. So if I know the x value, I plug the x value in and find the corresponding y value. So I want to find f of 4, not f prime of 4, but f of 4, the actual function. It's a point on this graph that we're trying to find the equation of the line that's tangent to that point. So I'm going to plug 4 into my original function. So that's the square root of 4 plus 40. Square root of 4 is 2. 2 plus 40 is 42. That's the other part of the coordinate. So again, this is going to be my m, my x1, and my y1. Plug all that into my point slope form, and I'll get the equation of my line. So we're looking at y minus y1 is going to be 42 equal to m, which is 1/4, times x minus x1, which is 4. And we could leave it in this form. This would be totally fine. But I prefer slope-intercept form, and I think that's generally the preferred form of a linear equation. So I'm going to simplify this. Y minus 42 is going to equal 1/4 x. And then 1/4 times -4 is -1. And now I'm going to add that 42 over. And that's going to leave me 1/4 x. -1 plus the 42 is going to make 41. This is the equation of the line that is tangent to this curve at this particular point. Okay, so let me just show you graphically again what we've done here. Make this all make sense. So the curve that we're looking at is the square root of x plus 40. Let me graph this. Square root of x and then a plus 40. Here's the curve that we're looking at. Now it's shifted, so I gotta move. Okay, so there's our curve, right? What we're saying is let's focus on the slope at the x value of 4. And we said that that x value of 4 corresponds with a y value of 42. So this is, zoom out so you can see a little. All right, so this is the point we're looking at, okay? So at x equals 4, the corresponding y value of 42, that's the point we're looking at. What we just found is that the slope of the line tangent to that point is 1/4, and actually we found the equation for the tangent line. So now if I put this equation of this tangent line in, y equals 1/4 x plus 41, I can see exactly what I've done. Again, I have found the equation of the line that is tangent to that curve at that particular point. So it's an extra step, right? We were finding the slope, and now we're writing the equation by using our point slope form. Okay, so hopefully it makes sense, all of what we've done there. And we're going to do so much more of that, so hopefully you just love the process. Now, sometimes finding a derivative isn't possible. There are a couple of stipulations, a couple of places where we can't differentiate or we have functions that are not differentiable. So I just wanted to make sure that we saw these scenarios. So the existence of a derivative. The derivative exists. It's gonna happen when a function, let's again call it f, satisfies all of the following conditions. So we're only going to be able to differentiate or have a function that's differentiable or be able to find a derivative if we have a continuous function, so it can't be discontinuous. It's got to be a smooth function. The graph of it is smooth, meaning we won't see any sharp corners. and it cannot have a vertical tangent line. So if any of those three things happens, if it's discontinuous, if it has a sharp corner so it's not smooth, or it has a vertical tangent line, then the derivative does not exist. So it does not exist when any of those things occur. So if you look at the picture, we have some places where we would not be able to differentiate because one of the three conditions is applied. So we're looking at here a sharp corner, a sharp corner. Any of those sharp corners, those disqualify us from being able to differentiate. If we have a discontinuous function, that means our limit isn't going to exist, right? That's why we use this as a disqualifier. So if it's discontinuous, like we have here, a discontinuity in that, again, not going to be able to differentiate. Also, if we have a limit that doesn't exist, so here another discontinuity, like an asymptote, not going to be able to differentiate. And then if we have, what we see here is a vertical tangent line. So the tangent line at this inflection point, hopefully that word sounds familiar, is no good, right? If we have a vertical tangent line, we're not going to be able to differentiate. And in this last one, this picture here, the function not being defined, is not continuous, right? If we'd have to jump over the hole in that graph in order to continue tracing, so that discontinuity disqualifies that spot from being that function from being differentiable at that x value. Okay, so if we see one of those things occurring on a graph, it's not something we can find a derivative for. But in general, we're going to be finding derivatives. Okay, so when we're finding derivatives, we're finding slope, specifically the slope of a tangent line that is an instantaneous rate of change. Okay, so I hope you've got enough to get going on your assignment, but as always, if you have questions, feel free to reach out. Until next time, take care.